reagent over once, maybe twice, and there's like a 10 or 15-minute delay on the Bradford reagent. We have to set it up and it has to sit for a while. So things can go fast, they can go bad. I see that most of you found the grading sheet up there that has the grades that I've listed. Now, if the grades up there don't match what I've handed back to you, tell me and I can correct it. Other thing is, I got this nice sheet of pre-log questions with no name.
How'd they do?
4 for 4 on the first one, 0 for 2 on the second.
Never mind.
So if that looks like your handwriting and you don't have grades up there for the pre-lab questions, come up here, put your name on it, and toss it back in the box. Okay, so today we're doing essentially 2 related labs because they're both spectrometry, but they're actually work quite differently. So the Bradford reagent I have written over here because all the equipment for the Bradford test is on this bench or back by the sink. NADH lab is over there on those 2 spectrometers, and all the equipment you need for those is over there. So I've split it up like the room is set up. Now, one reason for doing this is that NADH lab, when you're measuring NADH, you're measuring at like 355 nanometers. And the spectrometers here won't do it. So when you're doing the NADH lab, you have to use these spectrometers. So you have to use this setup. The Bradford can actually be done on any of the spectrometers, but we'll kind of concentrate the Bradfords on the ones over here. If everybody gets done with this and these machines are free and we still have groups waiting to do the Bradford, they can shift over to here if they have to. Okay, so let's start off with the Bradford. Bradford is a way of measuring protein concentration. Oh, I suppose the next thing I should mention, we're doing both of these because they're kind of the key elements in what we do next week. And next week we start actually trying to isolate LDH from heart tissue. Anybody get a heart from me yet? Or am I going to have to go buy one sometime?
I've asked. I haven't got you one yet, but I've trying.
Try. Okay. But these 2 spectrometry techniques are basic for the analysis of what we get out. We won't need to do the spectrometry this week or next week, but the following week we'll again be hitting the spectrometers. And so this is the key, so you can use the spectrometers in 2 weeks to analyze your LDH. Okay, so the first thing we need to know when we're actually doing the LDH is we want to know its concentration. And that's what the Bradford assay is for. The Bradford assay is a mixture of a strong phosphoric acid and a dye. And the dye is normally a deep reddish color when it's not bound to anything. But with the strong acid, if you have any protein in there, the strong acid gives it low pH. And as you've been learning, whenever you go to low pH, the proteins become positively charged because you stick all the protons on. And once it becomes positively charged, that dye binds to anything that's positively charged. So dye shifts from an absorbance max in the red region, 465, and one in the blue region, to 595. So all you're going to be doing is looking at the 595 nanometer absorbance, making a calibration curve, and using that calibration curve to come up with a concentration of one of 4 different unknowns. The procedure as written is pretty much correct. I think somewhere in there it might say that you're using 5 mils of Bradford. That's actually 3 mils of Bradford. But the way they have the curve set up works just fine. I will tell you right now that the unknown is a high enough concentration that if you use 100 microliters or 50 microliters of your unknown, it won't work. It'll be too high in absorbance. So it's going to be something less than 20. And as the procedure is set up, it has 3 different blanks for your unknown. So you just go in and you say, well, Dr. Z said it's not going to be more than 20. So try 20, try 15, try 10, maybe try 15, 10, and 5. But the whole idea of an unknown is you don't know what it is, so you have to try several and see which ones work. Okay, the actual analysis is, let me kind of walk you through it. The first thing you're going to do is make this calibration curve. And with the calibration curve, you're using a protein of known concentration. So with the calibration curve, you're setting up like 10 test tubes, 7 or 8 test tubes, and you use a protein standard. BSA stands for bovine serum albumin, that's here. And it's in a 1 milligram per milliliter solution, and 1 milligram per milliliter is the same as 1 microgram per microliter. So when you deliver 10 microliters, you're delivering 10 micrograms. And for that, you're going to be using probably, depending upon which one is going to be the most accurate, either the P200 or the P100, P20. And each spectrometer should have a set of P20 and P200 in front of it. There are tips for them. Notice that you two guys have boxes that don't have tips. You're going to fill the bag with, take tips out of the bag and fill the racks as you need them. When you're done with the tips, all of them can just go in here. Now, the first thing you do is get a test tube with all of your standard set. Now the next thing you do is add the Bradford reagent. Bradford reagent is back here. Now this is in something called the repipette. And the repipette is a way of accurately giving yourself 3 mils of Bradford every time. So all you do is come back here, you grab it, you lift the plunger to the top, you squeeze down, try again, squeeze down, and from now on, every time you lift it up and squeeze down, you'll give yourself 3 mils of Bradford reagent. Now, Bradford reagent is an acid and a dye, and I just squirted it on myself, so you can probably see my fingers starting to turn a little bluish. So if you're going to use this guy, I would advise you to use gloves or rinse it off. You know you've got some on yourself. Yeah, Bradford reagent is working. Now, after you've mixed it, then you go over here and you take your test tube and you put it on the Vortex mixer. You have a test tube in here. A chemistry drawer. You should have a bunch of test tubes. And so now you'll have a little bit of standard, the Bradford reagent, and all you have to do is push it on there, and that mixes it up. And when your pre-lab questions was, how full should this test tube be? It shouldn't be over half full, because when you do that, it can blow up the top. Okay, so what you do is you set up that set of standards, and probably the best thing to do is set up your unknown at the same time, so you can put them all in the machine at the same time. You set them up, you mix them up, you let them sit for, I forget how much they tell you, but
10 minutes, I think.
What was that?
10 minutes.
10 minutes, let them sit for 10 minutes, and then you run to your spectrometer and you measure them up. Now the Bradford reagent will bind to anything, and that includes the glass or the plastic on your cuvettes. It will include sometimes the glass on your test tube if you let it sit too long. So one of the bottom lines on this one is, when you're through, clean out your test tubes, clean out your pipe, your cuvette as quickly as you can. Okay, but I would leave them all in there until you've completed your calibration curve, just in case something goes wrong in your calibration. Unknowns are in this one, so the box of unknowns is entirely separate from the DSA standard, so you don't get them mixed up. So here are your unknowns, A, B, C, or D. These spectrometers are pretty well work pretty well. The one thing, you've got instructions on your yellow manual on how to use these kind of spectrometers. The biggest problem that I have is I've given you small volume cuvettes. With a small volume cuvette, you don't actually need 3 mils, you only need about 1 mil. And the thing you have to keep careful eye on here is where the light is going. All the spectrometers have this little piece of tape that says the light goes this way. And with the light going that way, you want it to go through the long path length of the cell. So it has to go from here to here, going this way, not this way. So when you put them in there, make sure it's lined that way, not at 90 degrees. And if that's uncertain to you, come and ask. The other biggest problem that we have with this one is normally you zero your spectrometer, and over here we'll zero the spectrometer using deionized water. With the Bradford reagent itself has a pretty strong absorbance. So the big thing I've circled up there, zero spectrometer with the Bradford reagent. So if nothing else, you just go over, put a little squirt of Bradford, put it in there, and zero your spectrometer with that, not with deionized water. Otherwise, I'll be looking at your curve and saying, why does your first value start with an absorbance of about 7 or 0.7? Make sure you do that. Okay, so the whole idea is once you have your curve, you put in various microliters of BSA standard. Now the BSA standard is 1 milligram per milliliter or 1 microgram per microliter. So the first calculation on the table is how many micrograms of protein did you put in there? If you put in 100 microliters, you put in 100 micrograms, and we'll just make our calibration curve that goes from 0 to 100 micrograms. Recordance, absorbance, then you just go record the absorbance for all the other standards, and you should get a nice line of best fit. Once you have the line of best fit, you're going to put it in Excel on your own computer, y equals mx plus b, plug in your unknowns absorbance here into y, that calculate what x would be, and x will tell you how many micrograms of protein you had in that test tube. Then to go back to the calculation, you say, okay, I had maybe 15 micrograms of protein in that unknown, and what I did is I put 50 micrograms of protein in there, but I did that with, say, a 10 microliter sample. So you take your micrograms, divide by microliters, and that gives you concentration. Okay, so that's it with the Bradford. Over here with the NAD. NAD and NADH is one of the cofactors that everybody needs. It's not technically a vitamin because it's something that is so predominant in all food you eat, you don't need to actually have a vitamin pill to get it into your system. NAD is this structure here. You have a ribose sugar here, a ribose sugar here, an adenine base. So that part of it looks like a base from an RNA molecule. And then what we have is that's connected to another ribose sugar, and that ribose sugar is connected to this functional group. In this form, with a single hydrogen up here, it's called NAD+. In this form, what it does in biological reactions is it picks up an electron, and it picks up a proton. You put a proton on there, and you change it from NAD to NAD+. And this is one of the activities that our LDH does. Our LDH will shift this guy from NAD to NADH. In today's lab, what I've given you to start off with is NADH. Because NADH, this black one, has an absorbance here that is pretty good, pretty strong, around 355. So the way you guys over here are going to be telling how much NADH you have is you measure at 355 or whatever it says, and you just simply measure the absorbance, and the absorbance, by going through the calculations they have in the manual, using the epsilon value, will tell you your calculation, your concentration. On the other hand, when this guy shifts over to NAD+, that absorbance goes away because we changed the conjugated system up. As we change the conjugated system, we get stronger absorbance there and nothing out there at 355. This will become important in an assay we do for our LDH, because in that assay what we do is we add this guy that doesn't have an absorbance at 350. But as the enzyme does its work, it starts changing NAD+ to NADH, and we can tell how much enzyme is there by how much this guy picks up. But for today's lab, we're not worrying about watching things change, we're just worrying about what the absorbance is at that wavelength. Now this one, you don't have any standard curve because you're given an epsilon value. So you don't need it. You need about 3 mils to fill the cuvette. You've got larger volume cuvettes here, so you need 3 mils to fill the cuvette. And again, I don't tell you what the concentration of the unknown is because it's an unknown, you have to figure it out. But I will tell you that if you put in the unknown just straight in the cuvette, it will be off scale, so it won't work. So you're going to have to do some kind of dilution. And knowing that you need 3 mils in cuvette, simplest dilution would be maybe 1 mil of your unknown and 2 mils of water. But again, I would go ahead and set up 3 of these. Then maybe 1.5 mils of unknown and 1.5 mils of water, and maybe 2 mils of unknown and 1 mil of water. So you have 3 mils each time. You can stir it up, use a vortex if you want, put it in the spectrometer, and then measure the absorbance, and you're done. That's how fast this one is. You only mix up 3 solutions, and you put them in the spectrometer. It only takes you maybe 5 or 10 minutes to do that. So in fact, people over here, or the people who don't have a spectrometer, can start making up that solution right away. And as soon as somebody else is off the spectrometer, you can jump in on over here and do that. And even if you got both of those done, and these guys are still sitting around, you can go ahead and start making up these solutions and just wait for a spectrometer to open up and do it when you get a chance. General notes, don't trust any reading on these spectrometers with an absorbance greater than 1. Second one is your cuvette lined up correctly? These ones, it's still critical which way you line them up. And you still have to look on the spectrometer for which way the light's going. And these cuvettes, take a look at them. They've got one side which is kind of dribbly, and that's for you to grab with your finger. Then they've got one side which is clear, and that's the side where your light's supposed to pass through. So when you put this guy in here, this one, light's going this way. So you just put it in that. And as I said, on these, you can just use DI